Great. Let's get started. So yeah, I wanted to talk to you today about direct air capture. So it's really going to be more of an overview of the state of the art and the various technologies and where they're at in development and what that outlook looks moving forward as we transition to net zero. I want to dive right in and show you an example of what the largest scale DAC facility. It's actually currently under construction, but this is the Mammoth facility that Climeworks is developing. It's in Iceland. The capacity is set to be 36,000 tons per year of CO2 captured. They have another project which is actually in operation, Project Orca, which I'll show you another picture in a little bit. That is operational. That's, I believe, at 4,000 tons per year. But this is set to be commissioned in May of this year. You can see it's quite snowy and still under construction, but you can see up front those array of contactor banks, and the process hall is that structure there. But just to give you a feel of the scale that DAC is getting to today, at least for the current generation of technology. So at a high level, just an overview of the talk today to get you your bearings. So I want to talk a little bit contextually why we're talking about direct air capture, then dive into the landscape of technologies, look at some of the challenges and opportunities associated with DAC, talk about the cost of capture, which is a very hotly contested topic, talk about geographic considerations as well when we look at deployment, and then look a little bit at the activity to date in recent years, both for investment and public and private support for DAC. Alrighty, so why DAC? This first slide probably isn't much of a surprise to anyone on the call, but we do have a carbon budget we're running out, and any delay, well, we've been delaying global emissions reductions, and given the carbon budget, we need to make even more drastic cuts now, which also means that we need more carbon dioxide removal. So not just stopping our current emissions, but actively pulling CO2 out of the atmosphere as it stands today. The IEA actually just released their 2023 CO2 emissions report, which showed that emissions are actually still rising on an annual basis. So as of 2023, energy-related CO2 emissions hit over 37 gigatons of emissions. So that's still rising. You have that small dip there that was a result of the pandemic, but at least as it stands, while the trend is not increasing as much as it was, we are still going up in emissions on an annual basis, and we really need to obviously reverse that trend immediately. The plot on the right is just showing from BP's energy outlook a few different scenarios to show a range of different potential forecasts over the course of reaching 2050, and what that might look like for our current stated policies, which is more indicative of the new momentum there in green, all the way to a net zero scenario. Yeah, so I guess the point of the slide just showing, hey, we do have a fixed carbon budget and there is a time value on carbon, so we can't continue to delay. We need to act immediately and also look at carbon dioxide removal. Specifically on CDRs, so the IPCC in one of their latest reports has said we need to deploy CDRs to counterbalance the hard-to-abate residual emissions. That is unavoidable, so we can't just be reducing emissions and using traditional mitigation technologies like renewables deployment, energy efficiency, et cetera. We also need to be doing carbon removal. They've basically said the carbon budget will almost certainly be exceeded to be consistent with 1.5 degrees, emphasizing the importance for CDRs. So needing to do both that deep decarbonization and active carbon removal. Some of these hard to abate sectors, for example, aviation, marine, or other heavy industry, even agriculture, when you talk about CO2 equivalents, we will need some form of CDR at a gigaton scale to make sure that we hit our climate goals. This moves forward for me. There we go. So looking at DAC in comparison to some other carbon removals. So you have both natural climate solutions and engineered solutions. This is just showing one example from the ETC's report of a potential ramp up of CDRs over time, both cumulatively and on an annual basis. As you can see, kind of these broad classes, they gave some potentials, for the various technologies. When we talk about DAC, they're talking on the order of 100 megatons by 2030. If you look at the current pipeline of projects and how long it takes to develop a project, we're realistically about an order of magnitude less than that. We might hit closer to 10 million tons per year of CO2 removals from DAC by 2030, given the current projects in place and scale of development. I think IEA has looked at by 2050 achieving around a gigaton per year of DAC deployment. And if you look at historical learning rates, that may actually be feasible. You have to look at DAC in comparison to some of these other CDRs. There are opportunities, but there's also concerns. So we don't know what that pace and scale of cost reduction will be for DAC. It's expensive today. It also requires a lot of energy use for the current generation of technologies. Some of the other carbon removals, which you're likely aware of, natural climate solutions, you can achieve high potential, but there are some uncertainties in terms of the permanence of storage and the land requirements associated with that. And then, of course, bioenergy with CCS, another form of carbon capture, may have high potential, but there's also concerns in terms of making sure that biomass is sustainable and having enough supply relative to some other competitive uses. Alrighty. So diving into actual DAC technology. So the landscape is actually quite diverse. It's changed and evolved a lot. I've been looking at DAC for about the past 4 years, and there's been quite a lot of developments this decade. To achieve the large-scale gigaton abatement that we need, a lot of that's going to be through geologic sequestration. However, DAC does also provide a sustainable pathway source of carbon to produce synthetic fuels or electrofuels. Some of the main classes of DAC technology today, liquid solvents. So if you think of, which I'll get into more detail, the carbon engineering approach, you have these big banks of fans where you're blowing ambient air. It contacts a strong binding liquid like potassium hydroxide that captures the CO2. It then needs to be isolated. For example, in that process, the schematic on the top right, they're converting it they're forming a solid and then doing a high temperature regeneration or calcination to recover that CO2 and sequester it. Another class of technologies that a lot of developers are looking at is solid adsorbents. So also blowing ambient air through an array of filters, but these are solid filters with adsorbents present, where basically you go through a adsorption-desorption process. Once all that CO2 is collected and the sorbents are saturated, you would regenerate that either via pressure, temperature, humidity swing, and then repeat the process over again. And finally, there's a lot of emerging technologies, kind of next generation approaches, with the focus of wanting to make sure these are low carbon energy sources that are being used for DAC deployments. People are looking at electrochemical processes, so whether that's electroswing adsorption or regeneration of their process through electrochemical means, even membranes, passive carbonation, so not using fans, even direct ocean capture, if you've heard of that approach. So a lot of new developments in the DAC space. It's a very exciting area in terms of technology development. So I'm going to dive into a little more detail just on each individual class of technology, looking at solid adsorbents. So I have the schematic there on the top right. This is the Orca plant that I mentioned by Climeworks, based in Iceland. So this is currently the largest operating DAC facility in the world, 4,000 tons per year. You basically have these, you can see the fans on the back end that pull the air through, with the adsorbent filters inside of those containers. And they basically go through their regeneration cycle after they've been saturated. And all that CO2 is collected, and they have a partnership with Carbfix where they're doing their mineralization of that CO2. So they're actually permanently sequestering the CO2 that they are capturing. This is a few other examples of emerging solid adsorbent companies. Carbon Capture Incorporated, they have a technology agnostic approach. They're currently developing a very large project in Wyoming in the US, on the order of 5 million tons per year, and they plan to deploy that by 2030. But they basically, through with the philosophy that these sorbents are going to improve over time, and you may be able to change you want to be able to change those out as the materials improve and you get better performance and inherently lower the costs. So you can see there the example of them changing out these containers to where they would be able to switch those out and hopefully improve performance as the technologies develop. Carbon Collect is looking at a passive approach. So as you can see, there's no fans in this prototype. It's basically a retractable unit where that during the adsorption phase, the wind will blow the CO2 past those filters, and once they become saturated, it will retract and it goes through its regeneration process. The point being trying to reduce the energy requirement of direct air capture. Also showing global thermostat, they've recently deployed their demonstration plant in Colorado at 2,000 tons per year. So they have their proprietary monolith contactors that they're utilizing and looking to scale up. On the liquid solvent approach, Carbon Engineering is really the leader in this space. There's a few other technologies and companies that are in development, but lower TRL. I wanted to show this page. This is actually pretty remarkable in terms of the pace of development. So as of a year or two ago, Occidental Petroleum acquired Carbon Engineering, and they're looking to deploy their technology to help with their facilities. They do a lot of CO2 enhanced soil recovery in the Permian Basin in the United States. So they've basically FID'd and begun construction of a 500,000 ton per year direct air capture facility. So compared to some of the pictures I showed before, you can see they are really getting on at pace and scale. This is intended to be operational in 2025. But you can see even in that picture in the right, compared to the engineering or artist rendition, you can see the scale of these air contactors that are being built relative to maybe some of these cranes or trucks in that picture. So these are massive structures that are being developed, and it'll be really exciting to see in about a year or two's time how this plant begins operating and what that looks like. So very exciting development in the largest, certainly, project in development for DAC globally. Passive carbonation, I think, deserves its own explanation. So there are a few companies. Heirloom is getting a lot of press and it is very much scaling up at a fast pace. So they have a process whereby they're basically taking lime, so calcium oxide, or calcium carbonate limestone. They run that through a kiln. It's actually an electric kiln powered by renewable energy. So with calcination, you have to achieve very high temperatures on the order of 900 Celsius. But that calcination of the limestone yields your calcium oxide. by which can passively carbonate. So as you can see, their pilot facility in California, they have these very tall towers of basically just trays of calcium oxide, and I believe they hydrate it with water, so it's actually calcium hydroxide that is picking up the CO2 from the air. And that picture on the right is showing that limestone where they've pulled atmospheric carbon dioxide and basically mineralized and formed that limestone. So that limestone gets recycled back, goes into the kiln, and they have their cyclic process. And in that that calcination process, you're evolving CO2, and that would then go on to be sequestered permanently underground, or potentially used for other means. There are a couple other companies that are looking at passive carbonation. Origin is one of them, who's developing a calcium looping technology with their kiln and contactor as well. So this is definitely an emerging process approach, different than your traditional just solid adsorbent or liquid solvent, as I was mentioning before. Some other emerging approaches certainly worth noting. I think I indicated some electrochemical approaches. So Verdox has made a big splash and received a lot of investment. They actually have developed a process in a unit where you essentially have electrodes that are coated with a functional material that catches and releases the CO2 based on the voltage that's applied. So they're quoting much lower energy requirements than some of these other DAC approaches. They're at a lot lower TRL, but they're looking to scale that up. Holy Grail is another one on the bottom left there, where they basically are leveraging an electrochemical approach and have these modular contactors. Interestingly, they're focused on above ground storage. So that's, I guess, a picture of mineralized CO2 that they're looking to basically permanently store and do the monitoring, reporting, verification to ensure that CO2 stays where they put it. I guess on the bottom right, talking electrochemical, RepAir has received a good amount of investment and press on their approach. So they've developed a prototype, which is completely powered by renewables. So similarly, they're using, they have electrodes, which they're passing ambient air across. That CO2 is transported. They actually use a selective membrane that enables the capture of CO2. So that CO2 gets picked up by a hydroxide ion, turns into a carbonate, and is selectively transported across that membrane and ultimately released so that it can be used for sequestration or utilization. And then finally, membranes are also another area of development. Carburon is one company that is leading here. So they have a fast swing process where they cycle through basically using a membrane, but they modify their membrane fibers to their proprietary design to enhance the adsorption capacity of their materials. So a lot of different approaches. It's at this point, if I can say, no clear winners necessarily. Multiple generations, if you will, of development of these technologies, and it's all there's quite a few at a lower technology readiness level. There are some, as I certainly noted, that are farther along, but it'll be interesting to see in the next 5-10 years how this will all shake out and how we can bring the cost down for DAC. This is just a high-level slide looking at the value chain, if you will. So looking at the materials and components, this slide is certainly not all inclusive of all developers or companies, but just to give you a flavor of companies that are providing structure adsorbents, and there's other types of adsorbents. A lot of them are amine based, or even people talk about using metal organic frameworks. Zeolites are another material. Membranes, of course, as I mentioned. So various suppliers of these materials that could potentially go into DAC devices. And then looking at the system integration. So you have a lot of technology developers and companies that are looking at commercializing their technology across those various categories that I mentioned of classes of technology. You also have project developers. So a lot of these OEMs or DAC developers, they may be, at least in the early phases, developing their own projects, but in parallel and potentially in the future, they could be licensing out their technology or partnering with developers that do more project work. So in the case of Carbon Engineering and Occidental, they have their 1.5 is the company that's developing that project and looking to commercialize it. You have many other examples of companies, Strega, for example, that is looking at taking other companies' technologies and helping them to develop projects. There's various efforts for carbon storage. So I mentioned sequestration is a big play, and there's a lot of partners that are looking at doing sequestration. BP is one example of that. But you have other approaches. For example, I mentioned CarbFix, that's looking at more of a mineralization approach. Even other approaches like carbon built, looking at using sequestering CO2 in concrete in that manufacturing process. In addition to permanent sequestration, some companies are looking at utilization in the form of fuel. So using DAC as a sustainable source of carbon to ultimately produce your synthetic fuel. So even Carbon Engineering, as an example, is also, they have their, I believe it's air to fuel process to make a sustainable aviation fuel. Yeah, so quite a few players across the value chain in DAC. So that was a bit of the technology landscape. I want to talk more about some of the challenges and opportunities associated with DAC. So really the key question, right, is how do we achieve the necessary cost reduction and the scale up required to reach our net zero goals, and which technologies can overcome these challenges? So there are an increasing number of developers, researchers that are looking at finding the best solution. Some of the just apparent challenges with DAC, obviously the CO2 concentration. So when you look at carbon capture, you generally have point source carbon capture and direct air carbon capture being a few orders of magnitude less. So we're talking on a ppm level as opposed to a percent level, which obviously creates a challenge from a separation perspective. And at such a dilute concentration, you need a stronger chemical bond for that separation. You're also processing very large volumes of gas, which results in higher energy use. So some of the implications, at least currently, you have high capex, you have high operating expense for the equipment and all the energy use associated. On the topic of energy, this obviously needs to be low carbon intensity. So you're dealing with a lot of energy required, but we're also interested in having a positive climate benefit. You don't want to, some of these processes like solid adsorbents today, they're using a low grade heat. If that's from a traditional fossil source, there's a certain scope 2 emission or even scope 1 emission associated with that. And so you don't want to undermine the process that you're doing, emitting carbon just to pull it out of the air. So it really needs to be low carbon intensity. You start running into issues of, well, we want this plant to run 24/7 if it's only based in using renewable energy. How do we deal with that dynamic? So there are a lot of challenges from a process and project perspective beyond just the core capture equipment. The sorbent lifetime is another key challenge that developers and researchers are looking at. So, considering the thermal and oxidative degradation, traditionally amines have some challenges with oxidative degradation. So if you have a sorbent that is amine-based and you're contacting essentially ambient air, there are technical challenges with that. And inherently, if you're doing more frequent replacements of that sorbent over time, it's going to result in a higher cost over the project's lifetime and overall the overall cost of capture. So that's the key challenge, both in process design and material development that needs to be tackled. And finally, environmental co-impacts. So we're obviously doing this for a climate benefit, but you also have to take into consideration things like the water usage. If there are degradations of that material, what are there potential implications for the environment? What's the footprint or the noise? Those kinds of things. For example, it may be a good putting in an arid or desert environment may sound like a good idea for certain DAC technologies, but if it requires a lot of water and that's a water scarce region, that becomes an issue. I guess the one thing to note that the footprint of DAC is significantly less on a amount of CO2 sequestration relative to some of these natural climate solutions. Not to say that we shouldn't be doing NCS at large gigaton scale, but there are some benefits to these engineered solutions as well. In terms of opportunities and advantages at a high level, so I mentioned DAC. It's a form of CDR. It's able to provide negative emissions, which is actually not the easiest thing to do. There's only a certain handful of approaches that are able to do that, and as mentioned, we need CDR at this point to achieve our climate goals and tackle historical emissions. So that's a really big advantage and why people are talking about DAC. It can also, as an alternative, provide sustainable carbon feedstock for those fuels that are potentially could be developed. In terms of TRL, I believe I mentioned a lot of these developers are still at low technology readiness. However, that does mean, as an opportunity, there is a higher potential to lower costs. When you look at learning rates over time, these costs can come down. The plot on the right there, I'm kind of showing, and this is just a sampling I did a little while ago. There's certainly many more developers that are coming into the space, but this is just more indicative of showing various developers of different types of technologies and where they are on a technology readiness scale. As you can see, some companies, the likes of Climeworks or Carbon Engineering, they are deploying at more of an industrial scale. However, many of these emerging technologies are coming up at this gap between academia and industrial commercialization, which you may have heard of the term the valley of death. And we really need, if we want to achieve our climate goals, have large scale CDR deployment, we need more of these technologies to overcome this valley. One way of doing that, which is it's a challenge because at the end of the day, to develop these technologies, these startups need financing, they need investors, and they may present too much technical risk for an investor to provide their funding. And so one area in which we'll see is for governments to step in and give financing and grants, or for example, the US has had significant funding opportunities in recent years related to direct air capture and other climate technologies, can really help these companies, give them a chance to go up the TRL scale and actually make a profit and reach commercialization. But in terms of advantages, I mean, DAC, a lot of people talk about having a modular design, making it, a low complexity. A lot of these solid adsorbent technologies, you just have these contactors that go through a adsorption and desorption phase. If you make your systems modular and standardized, you can have offsite manufacturing, reduce the construction time and cost, which could considerably, if you're developing your supply chains at scale, can result in lower costs. Yeah, the redundancy of the modules can be simple to operate them, have high availability. There's also opportunity for heat integration. So the technologies that use low-grade heat, potentially integrating that with existing industrial facilities that have no other use for low-grade heat laying around, or maybe you have a heat pump and having the ability to use that. If you can do heat integration and lower the fuel input or the carbon intensity of that energy that you're using, you can improve your CO2 avoided cost. DAC also has the advantage of being flexible theoretically in the location that you put it. It doesn't necessarily need to be tied to existing infrastructure. Now there are certainly benefits, and I think in the first tranche of DAC deployments, they probably should be tied to existing or actively developed CCUS hubs. So if hubs are already being developed and have the transportation and storage infrastructure, DAC facilities can just piggyback onto that and lower their costs. But inherently, DAC is flexible in location as long as there's a place to store it. And then finally, another big advantage of DAC is the permanence of storage compared specifically to the natural climate solutions. It gives you straightforward accounting and can help you achieve permanent carbon removal. All right, and I wanted to talk a little bit just about opportunities in the research sense. So how can we best address the scientific and technical challenges of carbon capture for DAC? So dealing with these dilute sources. Just giving a flavor, a couple of years ago, the US DOE proposed a few priorities. They had a roundtable where they kind of all got together and spoke to some of these key research challenges and opportunities that could be had. So I just pulled out a few of these of potential interest from the capture side. So looking at, mass transfer and reaction. So how can we exploit those interfaces, enhance CO2 reactivity and mass energy transport of those? So understanding those phenomena and looking at how we can basically better understand that to design better processes and better materials. Actually creating new materials. So looking at the methods of actually producing them, and also looking at materials that have some of these challenges with CO2 being dilute. So having a high binding affinity, but also not requiring so much energy to release that CO2 from the material or do a chemical conversion, actually having durability. And it may have good properties or high CO2 capacity, but is it actually durable and able to implement into a industrial commercialized process? And then finally, just speaking to energy efficiency. So inherently with most CO2 materials, you have to capture that CO2, but then you have to release it. And so how can we look at potentially some unconventional ways of having that binding, but not requiring such high energies of release? So when you look at, for example, the heat of adsorption, can we look at clever ways of lowering the overall energy consumption for these direct air capture processes? Speaking to the cost of capture, so DAC, this is a very hot topic. The costs are high today. They're also uncertain. It really depends on the technology, the scale, what deployment it is, if it's closer to a first of a kind, closer to an nth of a kind project or technology. Even, there's a lot of studies out there, what parameters they're using or assumptions they're making. One study I'm quoting there at the bottom suggests, DAC could potentially fall to $100 to $600 per ton by 2050, which is obviously a large range, but there's a lot of ifs and things that depend if we can get to the lower or upper end of that range. A lot of developers claim the ability to approach closer to the $100 per ton end range. That remains to be seen, but hopefully with new materials and processes being developed and the scale up of DAC supply chains can help bring those costs down. In terms of cost certainty, even though there are a handful of DAC pilots and demos that are in development today, these are still relatively new, and a lot of that's not in the public domain. And so it makes it a challenge of understanding what the costs are today, truly. And so we're really hoping to have greater cost certainty near term with some of these pilots and projects being deployed. But we do expect dramatic decreases. So as I mentioned, some of these are first of a kind deployments or new technologies at low TRL. So we do expect, like other technologies, the costs to come down through scale up, learn by doing, optimization, as well as the innovation, improving the materials, the energy demand required, and even the cost of renewables. So if it's a fully renewable process, how much are the renewables costing will impact your project economics. In terms of demand today, there's actually quite a bit to help at least these early startups get off the ground. So the voluntary market demand is certainly present. There's a lot of government funding, as I was initially mentioning, and also available incentives in certain parts of the world. The U.S. is one of the large ones with their Inflation Reduction Act and the tax credits associated with that. So it's actually creating real financial opportunity for these developers and accelerating development of DAC technologies, which is really good. Just a quick comment on DAC relative to point source capture. So this plot on the right is showing the actual theoretical minimum workforce separation. So if you look at DAC relative to, say, point source from natural gas or coal-fired power plants, it's only about 3 times greater than point source capture, despite a couple orders of magnitude difference in the concentration. You still obviously have the energy of separation that's unavoidable, and we're trying to improve these energetics to within the bounds of thermodynamics. But one of the things that developers can do to help reduce costs is be more efficient with the bulk separation. So I mentioned supply chain or even the contactor design. So just more efficient processes to handle the air and in contact and remove that CO2. Supply chain is a big deal, and costs aren't going to get to the level that we want to without large scale development of contactors. We talk about the modularization, the standardization. If we can do that at significant scale, that will help to bring those costs down. This is just a little bit on favorable locations for DAC. On the left is just an example study that was done for the United States, but should be similar for most regions in the world at a high level, right? You need suitable geologic carbon storage for the scale of abatement that we're looking for. You want low cost, low carbon electricity. I mentioned industrial synergies, whether that's waste heat or tying into existing hubs and achieving economies of scale. Atmospheric conditions is an interesting one. Depending on the type of technology, you may prefer a warmer and more humid environment. For example, liquid, if you're actively contacting a liquid with air, you're going to have evaporative losses. A lot of solid sorbents, they have better performance in colder or drier climates, and so that might improve their performance and economics to place them in those regions. At a high level, we think a lot about hydrogen hub development. DAC might have similar locations in terms of, the low cost, low carbon electricity, or for blue hydrogen, geologic carbon storage. And then finally, having that low cost of electricity, it's required for DAC. And if you are going to do fuels production, that's also important. And I want to make sure I leave some time for Q&A. I think I just have a few more slides. But just want to speak to there's been a lot of activity in DAC in recent years, and a lot of investment. So kind of the headline here at the top, total investment has exceeded $3 billion. So there's a lot of these, I'd call them startups, but some of them are full-fledged companies at this point that are leading the way. Climeworks is one of the leading developers that I mentioned up front. They raised over $650 million in their last funding round. It was very significant money. I mentioned their progress with their plants in Iceland. They've won the DAC Hub funding award that was announced in the United States. So they're developing a megaton scale plant in Louisiana. Global Thermostat is one of the original developers of DAC technology. They've had significant private investment since their inception, and they're marching right along. I won't list all of these, but a few notable. I mentioned Carbon Engineering. Occidental acquired them. That was a $1.1 billion acquisition last year, and BlackRock proceeded to invest $550 million in that project that they're developing in the Permian Basin. So very significant amount of funds that are moving on across the technology landscape. So a lot of activity here. Just speaking a bit more to support, not necessarily completely from a financial perspective. Well, it's all related to finances, I suppose, but you look at these private and public areas of support. So privately, there's a lot of companies doing advanced market commitments where they're purchasing credits before they're generated. So if you have a DAC plant producing CDR credits, and these projects are in development, some of the ones I mentioned, these companies have already purchased those credits in advance, and they're selling out at very high premiums on the order of, close to $1,000 per ton. You also have government programs in place. I mentioned the U.S. Bipartisan infrastructure law funding. They allocate $3.5 billion for DAC hub development. You also have the UK government looking at more and more financing and grants for DAC technology. So a lot of activity here that is really encouraging for developers to help them get off the ground. Finally, this is just a summary slide, and then we can answer some of your questions. So just overview, right? We do need DAC, we need CDR in addition to, not instead of, deep decarbonation. So it's really important, given the technology readiness of these technologies, that we continue to invest and look at developing these to get them to commercialization so that we can achieve our climate goals. We have to act today. DAC is one of few negative emission technologies available, and we need it at a gigaton scale in the next 26 years. Global DAC capacity today is many orders of magnitude less than that, so we have a very long way to go. However, there are quite a few facilities that have been announced to be in development, which is really encouraging. I mentioned the liquid and solid approaches, but there are many emerging that could potentially be much more disruptive, which will be really encouraging and exciting to watch over time as those develop. The main point being, we really need these costs to come down drastically if we want to scale them up. There are incentives today to get that kickstarted, but we do have a long way to go, and those need to meet somewhere in the middle where the costs are low enough to where society can accept those costs and have DAC actually be viable at large scale. So I'll stop there, but hopefully you enjoyed that or maybe learned something new, but happy to take questions.